To a mathematician, beauty doesn't look like a perfectly balanced spreadsheet or a massive string of crunched numbers. True mathematical beauty is finding perfect, hidden order buried deep inside what looks like absolute chaos. Take a closed, finite system, like the tangled social web of this crowded high school classroom. If we wanted to understand how these people relate to one another, how could we possibly map every single connection between them? We start with something called a relation. In mathematics, a relation is the most basic, fundamental way to describe a connection between any two distinct objects. If you have an object in group A, and some recognizable link connects it to an object in group B, you have a relation. It doesn't matter what the link actually is. If a line can be drawn between them, a mathematical subset is formed. This definition is so permissive that it allows for total ambiguity. A student could be related to their desk, or their favorite color, or every other person in the room simultaneously. Without more specific constraints, we have a list of links, but no way to group or process the data. We need a way to filter this wild web of data into highly organized categories. Specifically, we're looking for a relation that behaves almost exactly like an equal sign, a way to group things that are, mathematically speaking, exactly the same. To get there, we apply three distinct filters. The first is reflexive logic. This means any given object must always relate to itself, looping back to its origin point. The second filter is symmetric logic. If a connection exists, it must run equally in both directions. If point 1 connects to 2, point 2 must connect back. The third is transitive logic. This dictates a chain reaction. If A connects to B and B to C, then A connects to C. When you force a messy set of data to follow all three rules simultaneously, the chaos disappears. The data instantly separates into isolated, self-contained islands. By applying these three rules, mathematicians force a sprawling universe of information to organize itself into predictable, rigid boxes known as equivalence classes. Sorting data into these classes creates order, but the system remains static. To build a system that actually processes and transforms information, we have to move from grouping objects to defining active rules. This brings us to the function. A function is a restricted relation that operates on a single rule. Every input you feed it is allowed to produce exactly one output. We can constrain this further with the 1-1 rule. Under this condition, no two inputs are allowed to land on the exact same target. Every result must be unique. Then there's the onto constraint. An onto function ensures absolute coverage. No potential target in the output group is left untouched. Every point in the final set receives an incoming line. When a function is perfectly one-to-one and onto simultaneously, we have a bijection. This creates a complete symmetrical map between two sets. A bijection guarantees perfect reversibility. Because every input maps to exactly one unique output, with nothing left over, mathematicians can translate information between different systems without losing a single data point. We've taken the loose, everyday idea of a connection and forged it into a rigid, highly precise tool. In any closed, finite system, like the students in our high school classroom, the results are predictable. If every student has exactly one unique desk and the room is full, a one-to-one function will inherently cover all the targets in the room. But what happens to these strict rules when we leave finite constraints and attempt to map the infinite set of all whole numbers? Take the function where you double every integer. F of x equals 2x. Every input creates a unique, even output, making it perfectly one-to-one. But because doubling skips every single odd number, it fails to be onto. Infinity breaks our common sense. Human intuition for quantity breaks down the moment sets become endless. In that environment, these rigid definitions aren't just technicalities. They are the only reliable way to distinguish between different types of infinity.